Okay, let's start this. Uh, if others join, they can follow up. So, as you all know, I am conducting this season because I am a PMRF fellow and we are required to deliver uh, studies related to our topic within a government recognized institution. I am Vishnu Kant Verma from IIT Bombay. I am a PhD scholar there. Uh, we will be solving chapter-wise solution of GATE examination, geophysics section. This is the chapter-wise methodology uh, along which we will follow the seasons. Like I will start with gravity methods, then magnetic methods, then earthquake seismology, explosion seismology, then electrical methods, then EM, well logging, signal processing, geophysical inversion. There are a few questions asked from radioactivity and heat as well. Then mathematical methods in geophysics, and in last, solid earth geophysics and planetary systems. So this is the question. We will start from year 2018 and we'll go backward. So here is our first question. It was asked in 2018 GATE examination in the section of gravity methods, common section, 1 marks question. The question is, the geoid can be best defined as, and the options follows are: an oblate spheroid that best approximates the shape of the Earth, a surface over which the value of gravity is constant, option C, the physical surface of the Earth, or D, an equipotential surface of gravity of the Earth. You guys want to try? You can write in the chat box. According to the definition given in the book by Fundamental of Geophysics in William Lowry, they have stated that geoid is a physical equipotential surface of Earth gravity. The equipotential surface shall be physical. Like for a homogeneous Earth, there will be homogeneous spheroidal Earth. There will be infinite number of spherical surfaces that are equipotential. But geoid is that one that is physical equipotential surface. So here D is the correct option. An equipotential surface of Earth gravity is termed as geoid. Our next question is again 1 marks question, gravity 2018. Which one of the following corrections is always added during reduction of the observed gravity data? Always added. We know that free air correction can be positive or negative. Google correction can be positive or negative. Whether the elevation measurement station is above the datum or below the datum. Latitude correction can also be positive or negative, but the terrain correction over the land is always positive. So correct option is D here. Effect of terrain is basically to reduce the earth gravity. So we want to correct for this reduction by increasing the value. There is one fact you guys can remember. Whenever there is an effect that is causing gravity at a point to decrease, we call it the effect is negative, and we shall apply some correction that compensate for the reduction. So if the effect is negative, the correction is going to be positive. So terrain correction is always positive. Here is the third question, but this is from the geophysics section, 2 marks question. In the figure below, Z denotes the depth to the center of a buried sphere. This is the sphere, this is the surface. Depth, we are having depth Z below the surface of the Earth, such that Z is the distance between the surface and the center of the sphere. And we know the gravity anomaly due to a sphere has a Gaussian shape like this. So in this question, they have asked if Z is the depth and X half denotes the half width of the profile. Half width means uh, this value where we are having G max by 2. So they have asked what is the ratio of Z to the X half. And for a sphere, we know the ratio is 1.3. For a cylinder, the ratio is 1. We are talking about half width at half maxima. The answer will be different if they have asked about the full width at half maxima. Our next question is again from geophysics section. Suppose there are two survey vessels with ship-borne gravimeters that are cruising toward each other at a speed of 6 knots each along an east-west course. The difference in gravity readings of the two gravimeters is 63.5 milligal at the point at which survey vessels cross each other. The latitude along which the survey vessels are cruising is. For solving this question, we need to know about the Itovo's correction. We apply Itovo's correction whenever there is some movement of the measuring vehicle, whether it is airborne or shipborne. In the present scenario, it is shipborne. And there are two survey vessels. Speed is given in knots. We know that 1 knot is 0.5144 meter per second, and they have given that the vessels are cruising across east-west course. Means uh, whenever in the formula you will find there is a factor that is related through the east-west course. So we will put that there. The difference in gravity reading of the two gravimeters is 63.5 milligal. Okay, so if G1 is the gravity measured by the vessel 1 and G2 is the gravity measured by the vessel 2, the difference in their relative reading means G1 minus G2 is 63.5 milligal. So they are basically asking about the latitude along which the survey vessel are cruising. Let's see how we can solve this. As I have pointed already, G1 and G2 are the individual reading measured by the two ship-borne vessels. So G1 minus G2 equals delta G. This is the formula for Itovo's correction. 75.03 V sin alpha cos phi plus V square by R, where V is the velocity of the vehicle, alpha is the vehicle heading angle with respect to true north. In the present scenario, you may note that they have given that vessels are cruising along east-west course. So the angle east-west direction made with the true north is 90 degree. So we'll put alpha equal to 90 degree. And they have asked about the latitude at which the vessels are moving. And the next term in this formula is V square by R. V is again the velocity of the vessel and R is the radius of the earth. And again they have given that the delta G reading is 63.5 milligal. Okay. We have just put here the value of V. Since the two vehicles are moving toward each other, their relative velocity will add like this: 6 minus of 6. Then sine of 90 degree means alpha. Alpha was the vehicle heading angle with respect to true north. And we have to determine the value of phi. And the value of R from here, if you take 1 by R, you will get 0.04154. Again, here V square is the relative V square. So 6 square in one, but minus 6 square in another. So they just like they add on the power to the 1, they will subtract on the power to the 2. Pawan, you want to ask something? Pawan, if you don't want to ask anything, you can mute your mic.
మా దగ్గర
Okay, we were here. 1 milligal is equal to 10 gravity units, and this formula gives us the value of delta G in the gravity unit. So we need to convert milligal into gravity units. So 63.5 milligals equals 635 gravity units. Okay, then 75.03, 6 minus 6 equals 12, sin 90 cos phi. This term will become 0. So while solving this, we get the value of cos phi equal to 0.698. That turns out to be phi equal to 45 degrees. So these vehicles are traveling at a latitude of 45 degrees. The next question is again from the geophysics section, 2 marks question. The question goes like this: a gravity reading is taken in a stationary helicopter that is hovering 1 kilometer above mean sea level at a particular location. The difference in the value of G measured in the helicopter and at the mean sea level vertically beneath the helicopter is in milligal. We know that whenever there is a measurement of gravity taken at a elevation h with respect to the datum, we apply the free air correction. So if there are two measuring gravimeters, one is measuring gravity at the datum and one is measuring gravity at 1000 meter above that point, we will get a difference in gravity, and that gravity difference contributes because of the free air correction. So free air correction is given like 0.3086 times h, where h is in meter. So when we put the value of h, that is 1 kilometer or 1000 meter, we get the gravity value as 308.6 milligal. And this was a numerical answer type question. You don't have any options. You need to enter this value using the numeric keypad provided during the examination. Now we are covered. Now we have covered the gravity, all the gravity question asked in year 2018. Now we are moving toward year 2017. Common section means 1 marks question. They have asked about to match the quantities in group 1 with their units in group 2. So here there are various quantities like transit type, conductivity, gravity anomaly, magnetic field intensity. Since we are covering the portion of gravity, I am interested in answering the question related to gravity. So gravity anomaly is measured in milligauss or nanotesla or Simon or millivolt or microsecond per feet. I think all of you must be knowing the answer about it. We have solved some previous question where we were measuring the gravity anomaly in milligauss. So this is the right answer. Gravity anomaly is measured in milligal. When we are covering magnetic methods, then I will again show you this question, so you may know that the magnetic field intensity is measured in nanotesla. This is the next question, again common section, 1 marks question, 2017. The normal gravity formula, example for GRS 80, is a function of geocentric latitude or geodetic latitude or longitude or altitude. So there are two options that may be confusing, the geocentric latitude or geodetic latitude. And longitude and altitude, you all know, didn't appear in the international gravity formula. So the confusion between geodetic latitude and geocentric latitude can be removed by looking at this figure. Suppose this is our Earth, an oblate spheroid, and this is equatorial plane. Then the geodetic latitude is defined as this angle, and this angle is the angle between equatorial plane and the normal to the ellipsoid here. Normal to the ellipsoid means this surface, whereas the geocentric latitude is the angle between equatorial plane and the line joining the observation point, this point, to the center of the ellipsoid, this. So our gravity formula, international gravity formula, is a function of geodetic latitude and not the function of geocentric latitude. There can be a question formed where we can be asked that among the geodetic or geocentric latitude, which will be larger. So as can be inferred from this figure, if you see, geodetic latitude is always greater than geocentric latitude. Now this is the question from geophysics section, 2 marks question. Consider a geological body buried at the equator at a certain depth. If the same body were to be buried at the North Pole at the same depth, how would the gravity and magnetic field response measured over the body will differ? Assume the same magnetic susceptibility and density contrast. And we have to consider only geomagnetic induction. We need not consider the remanent magnetization. As you all know, the gravity formula due to any shaped body, for example, sphere, is a function of the shape of the body and its depth and density contrast. It does not matter where that body is located, whether it is at North Pole or at the equator. So, according to me, the gravity response shall not change whether the body is located at North Pole or equator. But we also know that magnetic anomaly is a function of inclination, declination. So, at the equator, we will be having different value of inclination and declination, but at the North Pole, those value will differ. So the magnetic field anomaly will certainly going to differ as compared to that at the North Pole or at the equator, but gravity anomaly will remain same. These are the options, but gravity and magnetic field response do not change. So this is wrong. Gravity field will not change, but the magnetic field response will significantly change. Option B, but gravity and magnetic field response change significantly. Again, this is wrong because the gravity field anomaly will not change. Option C is gravity field response changes significantly. Again, wrong. Last option is gravity field response does not change. Yes, but magnetic field response changes significantly. Yes. So correct answer for this question is option D. This is the 2 marks question, geophysics section, year 2017. This was again numerical answer type question. We are given the Buber density of 2 gram per cc and the Buber correction for a gravity station at an elevation of 30 meters above the datum. Is they have asked about the Buber correction. We know that the formula for Buber correction is 2 pi g delta rho times h, where g is the universal gravitational constant and delta rho is the density contrast of that body with respect to surrounding rock, and h is the elevation of measurement station with respect to local datum. Here they have provided the value of density contrast 2.8 gram per cc and the value of elevation as 30 meter. Just put those values delta rho here, h here, and the value of 2 pi g is remarkably 0.0419. If you put the value of g is equal to 6.673 into 10 to the power of minus 3, this will give you the value of 0.0419 for the density contrast in gram per cc and height in meters. So the correction comes out to be 3.5196 milligram. If you guys are having any questions, just raise hand or write in the chat box. If you think my speed is fast, then I can go a little slower. Just let me know. This is the geophysics section of year 2017 in gravity methods. The question goes like this: the ratio of eccentricity to the polar flattening of an ellipsoidal Earth with equatorial radius E and polar radius P can be expressed as. Uh, for solving this question, you need to know the formula of two things. First, eccentricity. For an ellipse, eccentricity is defined as square root of 1 minus semi-major axis to the semi-major axis whole square, where polar flattening is defined as difference of equatorial radius minus polar radius to the equatorial radius. Let's see how can we solve this question. Eccentricity is root over 1 minus p square by e square. P is the semi-minor axis and E is the semi-major axis of an ellipse. So by writing this in this form, this becomes E plus P times E minus P whole divided by E. And the polar flattening is defined as the difference of equatorial radius to the polar radius divided by equatorial radius. Again, this can be written in this form. E minus P can be written as the square root of E minus P times E minus P. Now, we have been asked about the ratio of these two, eccentricity to the polar flattening. If you closely see this formula, you will see that E will be cancelled from both of them. Under root of E minus P again will be cancelled from both of them. We will be left with square root of E plus P over E minus P. Now we have covered the gravity methods question of the year 2017 and 18. Now we are going in the year 2016. This is the common section question, 1 mark. According to ARE's model, gravity anomalies for fully isostatically compensated topography are characterized by. They have asked about the ARE's model, and they have given that the compensation is fully isostatically compensated, are characterized by negative Bunker anomaly, positive free air anomaly, positive Booger anomaly, negative free air anomaly, zero Booger anomaly, negative free air anomaly, positive Booger anomaly, or zero free air anomaly. For solving this question, I will be referring you to the two figures in the book by William Lowry. These are the figure number 2.44 and 2.57. Uh, Consider there is a topography below which we are having a normal crustal depth, and this is the root of that topography. And if this is fully isostatically compensated, we will be having the delta GI value equal to 0. No isostatic anomaly, fully compensated. And we know that delta GI equal to delta GB minus delta GR. Booger anomaly minus computed anomaly of root zone estimated from topography. If the isostatic anomaly itself is 0, these two will be equal. Delta GB will become equal to delta GR. And we also know that delta GR is the negative anomaly of root zone estimated from topography. So this is proportional to the negative of free air correction. Over a topography like this, we will be having a free air correction. So the delta GR will be negative of that. So delta GR will be negative because free air anomaly is positive. And we know that whenever we are having a free air anomaly, we will be landing with a negative of Booger anomaly. In this figure, it can also be seen that we are having a mountain, and then the normal crest, then the root zone of the crest, and below that mantle. If this is fully isostatically compensated, we can see that from the delta G value, that free air anomaly will vary like this, but it will always be greater than 0. But the Booger anomaly will vary like this. It will always will be negative. So the answer to our question is, over a fully isostatically compensated topography, we will be having a negative Booger anomaly like this and a positive free air anomaly like this. Okay, someone asked a question I missed, sorry. Brother, can I know the difference between your lecture and GATE previous year question and answer? Um, Again, I will be covering the GATE previous year question and answer in these lectures only. So if you are already covered those, you need not attend all the lectures. Anyway, I will be providing the recorded lectures of this. So if you have the book of that previous year solved question, you can go with that. Or if you are having any doubt in any question, you can ask or interact with me here. I will be happy to solve the same. So the next question is from geophysics section. The question goes like this: the value of free air correction, assuming sea level as datum plane, at an elevation of 150 meter is. Again, we know the free air correction is given by 0.3086 times 150 meter. So on solving this, you get a free air correction value of 46.29 milligauss. The purpose of conducting these lectures is to solve this question with you guys. So whenever there is an interaction of any questions, discussion about that question, we will learn better. So I will appreciate if you guys contribute to the this class. Means ask questions, comment if I'm wrong at any place, and we will solve this question together. We are having our next question again from geophysics section, 2 marks question. We are having a spherical cavity of radius 8 meter uh, that has its center 15 meter below the surface of the earth. If the cavity is full of sediment of density 1.5 into 10 to the power of 3 kg per meter cube and is in a rock body of density 2.4 into 10 to the power of 3 kg per meter cube, the maximum value of its gravity anomaly is. For solving this question, we need to know the gravity anomaly of a spherical body buried in subsurface. So the formula is like this: delta G equals 4 pi 3 pi G times delta rho r cube by z square times 1 over 1 plus x by z का whole square is to the power of 3 by 2. We are given the value of delta rho, density contrast, with respect to host rock. Here the spherical cavity is having a density of 1.5 gram per cc, where the host rock is having a density of 2.4 gram per cc. So we know the delta rho. We also know the radius of that spherical cavity. They have provided us the value of z, depth to the center of the spherical cavity. Now, since we are asked about the maximum value of gravity anomaly due to this sphere, we need not consider this term, the term that varies with x profile distance. So we are only left with this term. As I have told you earlier also, the value of 2 pi g is 0.0419. So if you take 2 pi g out of from the 4 pi 3 pi g, you will end up with 2 pi 3 times 2 pi g, and the value of 2 pi g will know. Okay, so this is the term corresponding to 4 pi 3 pi g. Density contrast is 0.9 gram per cc. How? 1.5 minus 2.4. That becomes 0.9. And R is given as radius of 8 meter. So 8 into 8 into 8, 512. The depth to the center is 15 meter. 15 square to 25 square. So delta G max comes out to be 0.0572 milligal. This is the question from geophysics section. We need to match the items in group 1 with their corresponding correction applied for reduction of marine gravity data in group 2. If we have to correct for effect of rotating homogeneous ellipsoidal earth, which correction we will be applying? Drift correction, latitude correction, Google correction, or Eddington correction? Drift correction is applied for the correction of inelasticity of the measuring spring. So this cannot fit here. The effect of rotating ellipsoidal earth is correlated with the latitude correction. Okay. Google correction compensate for the uh, deficit of mass between mean sea level and the depth to the ocean floor. Ito's correction is applied whenever there is some movement of a measuring vehicle in ocean or in air. So P correct with latitude correction. Effect of deficit mass from mean sea level to average depth of ocean floor is included in the Google correction. Effect of relative motion of ship with respect to revolving earth will be correspond to Ito's correction. Effect of elastic creep of gravimeter spring system and earth tides will equals with the drift correction. So here is the correct table. Okay, this was the 3-year questions of gravity methods from 2018 to 2016. If you guys are having any doubts, please free to ask the same in the chat box itself.